Welcome friends. In this session we are going to discuss the other two desirable properties of an estimator. They are sufficiency and efficiency. First of all, we are discussing sufficiency. In many problems of statistical inference, a function of sample observations contains as much information about the unknown parameter as to all observed values. Consider an experiment with only two possible results, success and failure. To estimate the probability of success P, let the experiment is repeated n times and let xi equal to 1 if the ith trial is a success and xi equal to 0, xi equal to 1 if ith trial is a success and xi equal to 0 if the ith trial is a failure. Then we consider t equal to summation I from 1 to n xi. T equal to summation I from 1 to xi, the total number of successes out of n trials. This is enough to estimate the value of P, that is the probability of success. We are considering probability of success as P, probability of success equal to. So, you want to estimate the probability of success. So, to estimate the probability of success, it is enough to know how many successes are there in the total repetition of n trials. It seems unnecessary to know which trial resulted in success. That is, t equal to summation over I from 1 to n xi is sufficient to estimate the parameter P. The result of n trials x1, x2, etc. xn contains no other information about P than that contained in T. Then T is called a sufficient estimator of P. Hence, the conditional probability of x1, x2, etc. xn given summation I from 1 to n xi will be independent of the parameter P. That is, probability of x1, x2, etc. xn given summation xi from 1 to n summation xi, that is equal to T, that is P raised to sigma xi into 1 minus P raised to n minus sigma xi divided by n c t into P raised to sigma xi into 1 minus P all raised to n minus sigma xi. The value of sigma xi is equal to T. So, we are cancelling this, finally, we are getting 1 divided by n c t. That means, the conditional probability of x1, x2, etc. xn given sigma xi equal to T is independent of the parameter P. Hence, as a definition, a statistic T is said to be sufficient for the parameter theta if it contains all information about the parameter contained in the sample, or if the conditional distribution of any other statistic given the statistic T equal to R is independent of theta. Fisher-Neyman factorization theorem gives the condition for sufficiency. Let x1, x2, etc. xn be a random sample from a population with the PMF or PDF f of x theta. Then the joint PMF or PDF of the sample, usually called the likelihood of the sample, is L of x1, x2, etc. xn theta, that is equal to f of x1 theta into f of x2 theta, etc. into f of xn theta. Then the statistic T is sufficient estimator of theta if and only if it is possible to write L of the likelihood function L of x1, x2, etc. xn theta as a product of two functions, L1 of t theta into L2 of x1, x2, etc., xn, where L1 is a function of the statistic and the parameter alone, and L2 is a function which is independent of the parameter theta. If it is possible to write like this, the likelihood function, then t can be considered as a sufficient estimator for the parameter theta. So, using this theorem, we can identify whether a given estimator is sufficient for the parameter or not. For example, for a Poisson distribution with a parameter lambda, show that, or we can show the sample mean x bar is sufficient estimator for lambda. Random sample x1, x2, etc., xn taken from a Poisson population with the parameter lambda. To show x bar is a sufficient estimator for the parameter lambda, that is, x bar is the sample mean. Now, since x1, x2, etc., xn is the random sample taken, the likelihood function of the random sample L of x1, x2, etc., xn, that is equal to, since it is Poisson distribution with the parameter lambda, f of x lambda equal to e raised to minus lambda, lambda raised to x divided by x factorial. So, L of x1, x2, etc., xn is xn lambda, that is f of x1 lambda into f of x2 lambda, etc., into f of xn lambda, that is equal to e raised to minus lambda, lambda raised to x1 divided by x1 factorial into e raised to minus lambda, lambda raised to x2 divided by x2 factorial, etc., into e raised to minus lambda, lambda raised to xn divided by xn factorial, or e raised to minus lambda multiplied n times, that is e raised to minus n lambda, then lambda raised to x1 into lambda raised to etc., into lambda raised to xn, that is lambda raised to x1 plus x2, etc., plus xn, divided by x1 factorial into x2 factorial, etc., into xn factorial. That is nothing, e raised to minus n lambda, lambda raised to sigma x, or x1 plus x2, etc., plus xn. We can write it as n into x bar, because x bar is x1 plus x2, etc., plus xn all divided by n. So, x1 plus x2, etc., plus xn is n into x bar. Then into the denominator contains the values 1 by x1 factorial, x2 factorial, etc., xn factorial. Now, the likelihood function is just like a product of two functions. One is e raised to minus n lambda into lambda raised to n x bar, and into the second is 1 by x1 factorial, x2 factorial, etc., xn factorial. Here we can see the first one, e raised to minus n lambda into lambda raised to n x bar, is a function of x bar and lambda. We can consider it as L1 of x bar lambda into. The next is a function, that is 1 by x1 factorial, x2 factorial, etc., xn factorial. There is no parameter involved. So, that is a function of x1, x2, etc., xn alone. We can write it as L2 of x1, x2, etc., xn. That means here we got the likelihood function as a product of two functions. One contains the statistic x bar and the parameter lambda, and the next contain no parameter. Then by the Fisher-Neyman factorization theorem, we can consider x bar, that is the sample mean, is a sufficient estimator for the parameter lambda in case of Poisson population. Next, let x1 and x2 denote random sample from a normal population with the mean theta and variance unity. X1, x2 are two samples from normal population with the mean theta and variance unity, that standard deviation is 1. Then consider the statistic x1 plus x2. Consider the statistic x1 plus x2. And we can establish this x1 plus x2 is a sufficient estimator for the parameter theta. To establish x1 plus x2 as a sufficient estimator for the parameter theta by the Fisher-Neyman factorization, if it is possible to write the likelihood function of x1 x2 theta as a function of the statistic x1 plus x2 and theta into a function which is independent of theta, that is L1 of x, L2 of x1 x2. If it is possible to write like this, then we can say x1 plus x2 is sufficient estimator for the parameter theta. So, for that we are trying to get what is the likelihood function in this case. So, here the sample taken from normal population with the parameter mean theta and standard deviation. So, f of x theta equal to 1 divided by root of 2 by pi into sigma, that is 1, and e raised to minus of x I minus theta the whole square divided by 2 into 1 square, or that is 1 by root 2 pi e raised to minus of x I minus theta the whole square divided by 2. That is f of x I theta, f of x I theta. Okay. So, here L of x1 x2 theta is f of x1 theta into f of x2 theta, that is 1 by root 2 pi e raised to minus of x1 minus theta whole square divided by 2 into 1 by root 2 pi into e raised to minus of x2 minus theta the whole square divided by 2. That is equal to 1 by 2 pi, then e raised to minus 1 by 2 into x1 minus theta whole square plus x2 minus theta the whole square. That is equal to 1 by 2 pi into e raised to minus 1 by 2 into x1 square minus 2 x1 theta plus theta square, then plus x2 square minus 2 x2 theta plus theta square. This gives the likelihood function L of x1 x2 theta, that is equal to 1 by 2 pi into e raised to minus 1 by 2, then here x1 square plus x2 square minus 2 into x1 plus x2 into theta minus 2 into 2 minus 2 x1 theta minus 2 x2 theta, that is minus 2 into x1 plus x2 into theta plus 2 theta square. That is equal to 1 by 2 pi into e raised to minus 1 by 2 into x1 square plus x2 square into e raised to minus of x1 plus x2 into theta into e raised to minus theta square. So, this is 1 by 2, we can write it as e raised to minus of x1 plus x2 into theta into 1 by 2 pi into again into e raised to minus theta square into 1 by 2 pi into e raised to minus 1 by 2 into x1 square plus x2 square. That is, this is equal to e raised to minus of x1 plus x2 into theta into x1 plus x2 into theta minus theta square into 1 by 2 pi into e raised to minus 1 by 2 into x1 square plus x2 square. Now, again we are getting the first function, that is e raised to minus of x1 plus x2 into theta minus theta square, and that is a function of L1 of x1 plus x2 and theta, and the second one, that is L2, there is no theta, that is a function of x1 and x2. Since it is possible to write the likelihood function of x1, x2 as the function of x1, x2 and theta, and a function which is independent of the parameter theta, we can say y. We can say the statistic x1 plus x2 as a sufficient estimator for the parameter theta. In the next case, if t is sufficient estimator for theta, then any one-to-one function of t is also sufficient for theta. So, we can establish it as follows. Let h equal to g of t, h equal to g of t. Assume h is a one-to-one function of t, then t equal to g inverse of h. Since t is sufficient for theta, L of x1, x2 etc. xn theta equal to L1 of t theta into L2 of x1, x2 etc. xn. Since t equal to g inverse h, we can write as L1 of g inverse h theta into L2 of x1, x1, x2 etc. xn. Hence, L of x1, x2 etc. xn theta is the product of a function of h and theta only and a function independent of theta. Then by factorization theorem, h is also sufficient for theta. Next, we are considering one more problem. Let x1, x2 etc. xn be the random sample taken from a population with the PDF f of x theta, that is equal to theta x raised to theta minus 1 for 0 less than x less than 1 and theta greater than 0. Here to get a sufficient estimator for the parameter theta, the sample x1, x2 etc. xn. So, the likelihood function of the sample L of x1, x2 etc. xn theta equal to f of x1 theta into etc. into f of xn theta, that is equal to theta into x1 raised to theta minus 1 into theta into x2 raised to theta minus 1 etc. into theta into xn raised to theta minus 1, that is equal to theta raised to n, then x1 raised to theta into x2 raised to theta etc. into xn raised to theta into 1 by x1 into 1 by x2 etc. into 1 by xn. So, we can write it as theta raised to n into then x1 into x2 etc. into xn, that is product I from 1 to n xi raised to theta into 1 by x1 into 1 by x2 etc. into 1 by xn, that is 1 by pi I from 1 to n xi. So, here we can consider this as a function, first function, and 1 by pi I from 1 to n into xi as second function. That is, this is a function L1 of the statistic existing here is pi I from 1 to n xi and the parameter theta is also here into the second, that is 1 by pi I from 1 to n xi. There is no parameter theta, that is a function of x1, x2 etc. xn, let it be L2 of x1, x2 etc. xn. So, in this case the likelihood function is written as the product of two functions, one contains a statistic and parameter. The statistic involving here is pi I from 1 to n xi. Therefore, we can consider the product of the sample, that is pi I from 1 to n xi as a sufficient estimator for the parameter theta. Next, we have to discuss the other desirable property, that is efficiency. As we already seen, to estimate a particular population parameter, there may exist more than one unbiased estimators. The best among them or the most efficient among them is identified in terms of their variances. Consider T1 and T2 are two unbiased estimators of the parameter theta. Then there exist uncountable many unbiased estimators for theta. Then the question arises about the efficiency of the unbiased estimators. The estimator T1 is said to be more efficient than T2 if variance of T1 less than variance of T2. Let T be the most efficient unbiased estimator for the parameter theta, that is the unbiased estimator with the minimum possible variance. Then efficiency of any other unbiased estimator T1 of theta is defined as E of T1, that is equal to variance of T divided by variance of T1, variance of T divided by variance of T1. The efficiency of most efficient estimator is 1 and that of any other unbiased estimator is less than 1. The relative efficiency of T1 with respect to T2 is denoted by E and is defined as variance of T2 divided by variance of T1, variance of T2 divided by variance of T1. We are considering some problems. For the random sample x1, x2, etc., xn taken from a population with the mean mu, we have to test whether the following statistics are unbiased estimators of mu and to identify which is the most efficient estimator. The estimators considered are: number 1, 2x1 plus x2 all divided by 3, 2x1 plus x2 all divided by 3. Number 2, 2x1 plus 3x2 all divided by 5. And number 3, x1 plus x2 plus x3 plus x4 all divided by 4. Okay. The random sample are taken from the population with the mean mu. Now, first of all, to test whether the given statistics are unbiased for the parameter mu or not. So, expectation of 2x1 plus x2 all divided by 3, that is 1 by 3 into expectation of 2x1 plus x2, that is 1 by 3 into 2 mu plus mu. So, we are getting it as mu. Okay. So, first one is unbiased for mu and second one expectation of 2x1 plus 3x2 all divided by 5. Here also we are getting 2 into mu plus 3 into mu all divided by 5, that is again mu. So, second one also unbiased. The third one expectation of x1 plus x2 plus x3 plus x4 all divided by 4, that is 4 mu divided by 4, again we are getting mu. So, these three suggested statistics are unbiased for the parameter mu. Now, we want to identify which is more efficient. So, to find the efficiency or which is to compare their efficiencies, you want to find their variances. So, variance of 2x1 plus x2 divided by 3, that is equal to 1 by 9 into variance of 2x1 plus x2, that is 1 by 9 into 4 into variance of x1 plus variance of x2, since they are random samples. We are assuming the population variance is sigma square. If so, this is 1 by 9 into 4 into sigma square plus sigma square, that is 5 sigma square divided by 9. That is the variance of the first unbiased estimator. The variance of the second unbiased estimator, that is variance of 2x1 plus 3x2 divided by 5, that is 1 by 25 into 4 times variance of x1, that is 4 times sigma square, plus 9 times variance of x2, that is 9 times sigma square, that is equal to 13 sigma square divided by 25, and the variance of x1 plus x2 plus x3 plus x4 all divided by 4. Here we are getting it as 1 by 16 into variance of x1 plus variance of x2 plus variance of x3 plus variance of x4, that is sigma square plus sigma square plus sigma square plus sigma square, that means 4 times sigma square or sigma square divided by 4. So, among the variances of these three statistics, first one is 5 sigma square by 9, then 13 sigma square by 25 and sigma square divided by 4. Among this, the minimum is sigma square divided by 4, that is for the third statistic. So, the statistic x1 plus x2 plus x3 plus x4 is more efficient in this case. More ideas and concepts on statistical inference, including the estimation of intervals, etc., will be discussed in the next session. Hope you enjoyed this session. See you next time. Until then, goodbye.